Today we're going to talk a little bit more about horizontal and vertical tangent lines. First, we're just going to go over a couple of the things that we talked about last time. One being a horizontal tangent line can only occur when the derivative is equal to 0. And in order for that to actually yield a horizontal tangent line, the function must be defined at that x value, and there must be an open interval, no matter how small it is, surrounding that x value. Similarly, for a vertical tangent line, the derivative has to be undefined, but we're still looking for the function to be defined at that point and for there to be a continuous open interval surrounding that x value. But in addition to that, we have to think about what it means for a derivative to be undefined. For a derivative to be undefined, 4 different things could be happening. We could have a corner, like this. We could have a cusp, where we end up with something like this or like this. Or we could have a vertical tangent line, or we could have a discontinuity. In order for there to be a vertical tangent line, there has to be a change in concavity. So first off, we need to know that this, anything that looks like a parabola that's opening up is concave up. And anything that looks like a downward facing parabola is considered concave down. Now, we don't quite have the tools yet to determine when a function is concave up or concave down, but we'll learn that pretty soon. But we can note that at a corner, we're having 2 straight lines that are meeting each other, and therefore there's no concavity whatsoever. And at the cusps, we're going from, in this case, concave down to, again, concave down at the cusp, or concave up to concave up at the cusp for the other one. So we'd have to have a change in concavity, which means it's going to go from concave up to concave down when we have a vertical tangent line. Now, especially for implicitly defined relationships between x and y, we need to make sure that when we take this derivative, we don't end up at a certain x value with the form 0 over 0, form we've seen before. If we end up with 0 over 0 at any given point on our graph, that means that we do not have a horizontal or a vertical tangent line. There are quite a few different things that could be happening there, and we'll sort of talk about some of those a little bit later. But for now, just know that if we have 0 over 0, that's not a horizontal or a vertical tangent line. So that being said, if the numerator of our derivative is 0, but the denominator is not 0 at a given point, that means we have a horizontal tangent line, and vice versa. If the denominator of the derivative is 0, but the numerator is not, we'll have a vertical tangent line. So let's take a look at a couple of problems here. So we're going to try and find the equations of all of the horizontal and vertical tangent lines for x squared plus y squared equals x squared y. So this implicitly defined relation needs to be differentiated implicitly with respect to x. So we'll start with 2x plus 2y dy dx is equal to the derivative of x squared y, which has to be done using the product rule, x squared times the derivative of y, plus the derivative of x squared, which is 2x, times y. We'll do a little bit of quick rearranging here to get all the dy dx terms onto one side. So we'll have, and we'll also factor out that dy dx. We'll have dy dx times 2y minus x squared, when I bring that x squared dy dx to the left, is equal to 2xy minus 2x, when I bring that over to the right side. And then we just divide. Dy dx gives us 2xy minus 2x over 2y minus x squared. So we've got our derivative. And now our next step is to think about what values make this derivative equal to 0. And so as we talked about on the previous page, in order for the derivative to be 0, we need the numerator to equal 0. So we'll say dy dx is equal to 0 if our numerator 2xy minus 2x is equal to 0. That should be pretty straightforward to solve. We'll just factor the 2x out of it, giving us 2x times y minus 1 is equal to 0. And with the zero product property, we can see that that yields x equals 0 and y equals 1. So now we've got to go ahead and take each of those values and plug them back into our original equation. One of the sort of irritating things about implicitly defined relations is that oftentimes our derivative will appear to be 0 at some xy value or some x value or some y value. But when we plug that back into the original equation, we find that either there's multiple points that work for that x or y value, or that there might be no points that work for that x or y value. So we'll start up here. I'll do this in a different color now. If x equals 0, when we plug that in, what are we going to get? 0 plus y squared equals 0, or just y squared equals 0, or just y equals 0. So it's possible for us to have a horizontal tangent line. We'll say horizontal tangent line with a question mark. It's possible at the point 0, 0. We'll have to check later with our denominator to see if that still works. Then, now we'll plug in y equals 1. So if y equals 1, then we've got x squared plus 1 squared, which is just 1, is equal to x squared times 1, which is just x squared. This, I think pretty obviously, if you subtract x squared from both sides, if you 1 equals 0, which we can just pretty much say, no, that's just not true. So our equation here would like to have a horizontal tangent line when y is 1, but there's actually no value on our equation, on our graph, where y equals 1. So therefore, we can eliminate y equals 1 as a possibility. And we'll see an interesting thing that happens with the graph of this in just a couple of seconds when we graph it after we finish. So that takes care of possible locations of horizontal tangent lines. Now we're going to figure out when our derivative is undefined. So let's take a look at a new page. We've got our derivative as 2xy minus 2x over 2y minus x squared. So in order for this to be undefined, that could only occur if the denominator, 2y minus x squared, was equal to 0. Well, that one's a little bit more complicated because there's nothing good to factor out of it. But we could recognize the fact that we need this to be true, and we also need our original equation, which was x squared plus y squared equals x squared y, to also be true. Well, all that is just a system of equations. So if we take our equation over here on the right, 2y minus x squared equals 0, and solve for y, we end up with y equals x squared over 2. We can just go ahead and plug that straight in to our original equation and solve for x. So we'll have x squared plus, now since y is x squared over 2, we'll replace that with x squared over 2 squared. And then we've got x squared times another x squared over 2. Simplifying this out a little bit gives us x squared plus x to the 4th over 4 equals x to the 4th over 2. And now it's just a matter of getting everything to one side, setting equals 0, and factoring and solving. If you want to, you can multiply everything by 4 first to just kind of make it look a little simpler. So if you decide to do that, you'll end up with 4x squared plus x to the 4th equals 2x to the 4th. And we can then see that that will give us x to the 4th minus 4x squared equals 0. We can factor out the x squared. leaving us with x squared times x squared minus 4 equals 0. And you can either factor the x squared minus 4 as the difference of squares, or just recognize that that's plus or minus 2. And we've got x equals 0 and x equals plus or minus 2. So these are possible locations of vertical tangent lines. Now, we have to think back a little bit to what we had for our horizontal tangent lines, and the fact that we cannot have the same coordinate pair giving us 0 in the numerator of our derivative and 0 in the denominator. If we look back to what we did a little bit ago, one of our possibilities was x equals 0, which when we plugged it into the original, found that gave us y equals 0.00. Well, right here, once we've done it for a vertical tangent line, we got that same x value. No need to plug it back into the original. We know it's going to give us y equals 0. And we can see pretty easily that if we looked at our derivative up here, if we plugged in a 0.00 to that, we get 0 over 0. Therefore, we are not going to have a vertical tangent line or a horizontal tangent line at x equals 0. We'll just make a little note there. This makes dy dx 0 over 0. So we can eliminate that. Now all that's left is taking a look at x equals 2 and x equals -2. Well, we do need to plug those back into our original equation to make sure that our graph actually has points at 2 and -2. It doesn't really matter what those points are. We know that they don't match up over here with our horizontal tangent line possibilities, with things that made the derivative 0, because we would have found x equals 2 when solving that. So we'll just quickly say if x is 2, that would give us 2 squared, which is 4, plus y squared equals 2 squared, which is 4 again, times y, or y squared minus 4y plus 4 equals 0, which we can factor if we want, y minus 2 squared equals 0, which gives us y equals 2. So clearly there's a value of y equals 2, which means x equals positive 2 is the equation of a vertical tangent line. And then if we look at when x is -2, we'll want to make sure that works as well. -2 squared is again 4. We still have plus y squared, and again, -2 squared is 4. We get the exact same equation that we had up above. Clearly, this is going to yield the same value of y equals 2. And we can see that we have 2 vertical tangent lines. One of them is x equals positive 2, and the other one is x equals -2. So these, I'll just draw an arrow here, these are our vertical tangent lines. And that's all we were able to find for this one. There were no horizontal tangent lines. So we'll take a quick second here, just because I think it's good for us to see what these graphs look like. We had x squared plus y squared equals x squared y. And if we take a look at that graph, we can see, first off, that it sure looks like at x equals -2 and x equals 2, we have vertical tangent lines. Those are occurring when y is 2, right here and right here. And we'll note that the funny thing that was happening at y equals 1 is that our graph looks like it wants to have a horizontal tangent line at y equals 1, but since there's no possible location on the graph where y is 1, it's actually just approaching y equals 1, and we have a horizontal asymptote in both directions of y equals 1. And we can see that the strange thing that was happening, you can see the little gray dot at the origin. When we had x equals 0, y equals 0, we just have a singular point sitting right there at 0, 0. And we can't have a horizontal or vertical tangent line there because, well, there's no open interval on either side of a singular point. So that was the weird thing that was happening at 0, 0. All right, let's take a look at another one. We've got x times y plus x squared y squared equals y. This time we're only looking for the horizontal tangent lines, but it still is going to require us to take a look at when the denominator of our derivative is 0 to make sure any possible locations of those horizontal tangent lines don't also make the denominator 0. So let's use the product rule on xy. That should be x dy dx plus y times the derivative of x, which is 1. And then the product rule on x squared y squared, so x squared times 2y dy dx plus 2x times y is equal to dy dx. And we'll leave the y and the 2xy on this side. And we'll move everything else to the other side. And I'm going to factor out the dy dx. So I've got the 1 dy dx there. And as I subtract the x dy dx, we'll have minus x, and then minus 2x squared y. And that will give us a derivative of dy dx is equal to y plus 2xy over 1 minus x minus 2x squared y. And since we're asked initially for the equations of horizontal tangent lines, we'll just say this is equal to 0 if y plus 2xy equals 0. And we'll again factor y times 1 plus 2xy. And I just realized as we went through here, I missed this squared on there. I took the derivative of the x squared y squared. X squared times 2y dy dx. And then the derivative of the x squared is 2x, but I need a y squared on there. So that 2xy squared translate down to all these places. So that when I factor out that y from y plus 2xy squared, we have y times 1 plus 2xy. Sorry about that. And we'll set this equal to 0, giving us, in one case, y equals 0, which should be pretty easy to deal with. And in the other case, 1 plus 2xy equals 0, which we'll have to worry about just a bit here in a second. So talking about y equals 0 to begin with. If y equals 0, well, let's plug that back into our original equation. We get x times y, which would be 0, plus x squared times y squared, which will be 0, equals 0. Well, in the last one, we got an untrue statement. In this case, we got a statement that's always true, which means that the line y equals 0 is part of the graph of this equation. So we can think about it in the way that there's going to be some other weird stuff going on, and then also we've got just y equals 0, the horizontal line, the x-axis is a full part of this graph. And if we were to think about what happens if I plug y equals 0 into our denominator of our derivative, if y equals 0, we end up with 1 minus x. And the only thing that would make that 0 would be when x equals 1. So at every other location on the horizontal line y equals 0, other than at x equals 1, this has a horizontal tangent line of y equals 0. at x equals 1, something weird is going on. We'll take a look at the graph in a minute and see what that weird thing that's going on is at x equals 1 and y equals 0. So 1, 0, something weird. We'll just call it that for now. Okay. Then as far as 1 plus 2xy equals 0, we have the option of solving for x or solving for y. But a better choice here is to recognize that in my original equation, I've got an xy, and I've got x squared y squared, which is the same as the quantity xy squared. So if I just solve this for xy, yielding xy equals -1/2, I should be able to plug that into my original equation to give me -1/2 plus -1/2 squared equals y, or -1/2 plus 1/4 equals y, or y equals -1/4. And while it doesn't really matter what the x value is there, we do need to make sure that an x value exists there. And we also need to make sure that point does not make the denominator of our derivative 0. So let's plug y equals -1/4 back into our original equation. We get -1/4x plus -1/4 squared is 1/16. So 1/16 x squared equals -1/4. And similarly to what we did with the previous one, we're going to multiply everything by 4. This time we're going to multiply everything by 16. And we're kind of running out of room here, so I'm going to move that over to another page. So if I multiply everything there by 16, we're going to end up with -4x plus x squared equals -4, which gives us x squared minus 4x plus 4 equals 0, which we can factor to x minus 2 squared equals 0, which gives us x equals 2. So at the point 2, -1/4, we're hoping that we have a horizontal tangent line. But we do need to make sure that we check this in dy dx in the denominator of dy dx, right? So if we go back and look, we have 1 minus x minus 2x squared y. 1 minus, got what it was, 1 minus x minus 2x squared y. And so we'll plug in to make sure that that does not come out to be 0. 1 minus, and then x is 2, and then 2 times 2 squared, and -1/4. So again, we're checking this in the denominator of dy dx. And 1 minus 2 is -1. Negative times a negative, positive. We got 2 times 4 is 8 times 1/4. It's 2. So we got -1 plus 2, which is 1. And so clearly that didn't make the denominator of dy dx 0. And so we just have the one horizontal tangent line of y equals -1/4. And so we'll take a second and take a look at what the graph looks like. Okay. For this one, we had x squared plus y squared equals x squared y. And oh, that's our previous one. We had xy plus x squared y squared equals y. And so if we look at what's going on here, we can see, first off, that we do have that line of y equals 0 right across the x-axis. We can see that the weird thing that was happening at the point 1, 0 is the graph intersects itself at 1, 0. And that's one of the weird things that could happen when you get 0 over 0 in your derivative. And lastly, we can see we got a little local minimum here at the point 2, negative 1/4, where we have our singular horizontal tangent line. Right. And this one, we're just looking for vertical tangent lines. So we'll start once again by just taking a derivative. Derivative of 2x is 2, and the derivative of minus 3y is minus 3 dy dx. And then the derivative of x squared is 2x, and the derivative of y cubed is 3y squared dy dx. We'll solve for dy dx, so we'll you can bring them to whichever side you want. I'll subtract the 2 over to here, so I have 2x minus 2. And on this side, I will have dy dx factored out of a positive 3y squared when I bring that over, minus the 3, giving us dy dx is 2x minus 2 over 3y squared minus 3. And so from there, we'll just take our derivative and see when it's undefined. So we'll say this is undefined if 3y squared minus 3 equals 0. That's a pretty straightforward one to solve. If we add 3 to the right-hand side, and then the left-hand side, and then divide by 3, we get y squared equals 1, or y equals positive or negative 1. So we've got 2 possible locations where this thing might have a vertical tangent line. So first off, what happens if y equals 1? Well, if y equals 1, when we plug that into our original equation, we get 2x minus 3 equals x squared minus 1. And that's just a quadratic. X squared minus 2x, and then we'll add the 3 over, plus 2 equals 0. And that does not factor nicely. And if you make an attempt to use the quadratic formula to complete the square, you'll see that there are no real solutions to this. You can always tell by looking at the discriminant. Remember, the discriminant is b squared minus 4ac. So that'd be negative 2 squared minus 4 times 1 times 2. That's 4 minus 8, or negative 4. If the discriminant is negative, you know there are no real solutions. So there should be no point on here where y is equal to 1. We can move ahead from there and test what happens when y equals negative 1. And if y is negative 1, we end up with 2x plus 3 is equal to x squared plus 1. And we can subtract the 2x and the 3 over. X squared minus 2x minus 2 equals 0. And since I seem to be running out of room here, we'll take a look at that on the next page. But what we're going to do is complete the square. So that minus 2 that I had, I'm going to add it over to the right-hand side. And remember, when you complete the square, you'll take half of the b value and then square it and add that to both sides. So this now becomes a perfect square. X minus 1 squared equals 3. And if you square root, you get x minus 1 equals plus or minus root 3. And x equals 1 plus or minus root 3. So those are 2 possibilities for where we might have a vertical tangent line. And all we need to do now is take a look at our derivative again, which was dy dx is equal to 2x minus 2 over 3y squared minus 3. And make sure that neither of these x values also make the numerator of our derivative equal to 0. Well, 2x minus 2 equals 0 when x is 1. Neither of these are x equals 1. So these must be two different vertical tangent lines for this equation. And we'd imagine that it must have horizontal tangent lines when x equals 1. And we'll see that when we look at the graph here right now. So this time we had 2x minus 3y is equal to x squared minus y cubed. And taking a quick look at this one, we can see that it sure does look like that at x equals 1, here's x equals 1 straight through the middle of this weird little oblong looking thing. We've got three different places where it looks like we might have horizontal tangent lines. And if we were to go in and put in x equals 1 plus the square root of 3, and x equals 1 minus the square root of 3, we should see that those appear to be vertical tangent lines over here at these two values. All right, we've just got one more here to go today. So this time we're looking for both horizontal and vertical tangent lines. And again, we'll just need to take our derivative, 4x, and then minus 2xy will be minus 2x y dx, and then minus 2y using the product rule. And then y squared will become plus 2y dy dx. The minus 4, its derivative is 0, and the derivative on the right-hand side of 0 is also 0. So now we just solve for dy dx. We can leave the 4x minus the 2y on the left-hand side, and then move the other stuff to the right-hand side and factor out the dy dx. So we'll have a positive 2x as we bring that over, and a minus 2y. And when we divide, we get 4x minus 2y over 2x minus 2y. Or better yet, we could divide everything by 2 to get 2x minus y over x minus y. And so now we're just going to look for when is this equal to 0 and when is this undefined. So we're going to say here dy dx equals 0 if 2x minus y equals 0, which would give us y is equal to 2x. We'll deal with that a little bit more in a second. At the same time, I'm going to say dy dx is undefined if x minus y equals 0 or y equals x. I think right off the bat, we can look at both of those two equations that we got and say that the only time that y equals x and y equals 2x would be if both x and y were equal to 0. Otherwise, there's no way for both of those things to be true. So we can immediately say any values we get of 0 for x or 0 for y when we plug these back into our original equation can be disregarded. And we know it's not going to be a horizontal or a vertical tangent line there. And if we were to even go plug 0, 0 back in, we'd get 0 minus 0 plus 0 minus 4 equals 0, giving us negative 4 equals 0. Well, that's just not true. So there's no places where this derivative is equal to 0 over 0. And we can not worry about having to recheck any values we get for our horizontal or vertical tangent lines. So let's now check y equals 2x for our horizontal tangent lines. So we need to solve when does y equal 2x, and also 2x squared minus 2xy plus y squared minus 4 needs to equal 0. Well, if y is 2x, we'll just plug that in. 2x squared minus 2x times y, which is 2x, plus y, which is 2x, squared minus 4 equals 0, and solve. We've got 2x squared minus 4x squared plus 4x squared, and we'll just add that 4 over now, equals 4. Or 2x squared equals 4, or x squared equals 2, or x equals plus or minus root 2. So those are the locations where we would have horizontal tangent lines. Now, the equations of the actual horizontal tangent lines can be found by taking this and plugging it back into either one of our two equations. It could be either one, but it seems a lot easier to plug it into y equals 2x than to plug it into 2x squared minus 2xy plus y squared minus 4 equals 0. So here we'll get horizontal tangent lines of y equals positive or negative 2 root 2. And if we go ahead and do the same thing with y equals x into our original equation of 2x squared minus 2xy plus y squared minus 4 equals 0, we'll end up with 2x squared minus 2x times x plus x squared minus 4 equals 0. Or 2x squared minus another 2x squared is going to cancel out. We've just got x squared equals 4, or x equals positive or negative 2. We don't need to plug that back in because that's already x equals for a vertical tangent line. One thing we do need to make sure, though, is that if we do plug it back into the original equation, it actually yields us some y values. So if we had 2 times 2 squared minus 2 times 2 times y plus y squared minus 4 equals 0, that would be 8 minus 4y plus y squared minus 4 equals 0, or y squared minus 4y plus 4 equals 0. And I think we can pretty quickly see that we can factor that and get y equals 2. And if we did the same thing with negative 2, we'd end up with 2 times negative 2 squared minus 2 times negative 2 times y plus y squared minus 4 is equal to 0. This is 8 minus 4 is a positive 4. We have y squared plus 4y plus 4 equals 0, which is going to give us y values of negative 2. And we really should have done the same thing back over here when we said x is positive or negative root 2. We should make sure that this positive or negative 2 root 2 that we found here as our horizontal tangent line, if I were to plug these points in, it satisfies our original equation. And so let's real quickly make sure that's 2 times root 2 squared minus 2 times root 2 times y, which was 2 root 2, plus 2 root 2 squared minus 4 needs to equal 0. And here we've got 0 equals, well, root 2 squared is 2 times 2 is 4. And here we've got minus a 2 times a 2 is 4. And a root 2 times a root 2 is another 2, so 4 minus 8. And then here, 2 root 2 times 2 root 2 is also 8. And then minus 4 equals 0. So it looks like that worked out. And if we use the negative root 2 and the negative 2 root 2, we'd see 0 equals 2 times negative root 2 squared minus 2 times negative root 2 times negative 2 root 2, and then plus negative 2 root 2 squared minus 4. And we'll probably note here that this comes out again to be 4. A negative times a negative times a negative is going to be a minus. And all those values are the same. That's going to be minus 8. And then here with our negative 2 root 2 squared, that's going to be a positive 8 and a minus 4, which comes out to be 0. So we can see that the x and the y coordinates here did satisfy our original equation. So we can be guaranteed that we've got those two horizontal tangent lines. And if we go into Desmos, we should be able to take a look at what we've got here. Our original equation was 2x squared minus 2xy plus y squared minus 4 equals 0. And we had y equals 2 root 2, y equals negative 2 root 2 as our two horizontal tangent lines, and x equals root 2, and x equals negative root 2. Sorry, not root 2. X equals 2, and x equals negative 2 as our two vertical tangent lines. And so we can see there's the original graph in blue, this sort of elliptical shaped thing that's tilted on its axis. And we've got our horizontal tangent lines at y equals 2 root 2 and y equals negative 2 root 2. And our verticals at x equals 2 and x equals negative 2.